Thank you all for being here. We had around 280 applications for this workshop, and we had the selection was very difficult. So we ended up having around 25 or 29, as Ramar said, participants to this workshop. So hopefully it will be beneficial. Perhaps some of the information we're going to present you're familiar with. So don't hesitate to participate in the discussion and give us your experience, or especially that I see that already we have people who has been doing some empirical research and has been also working on some microeconometric techniques. So don't hesitate to participate with your hand-on experience, because this at the end of the day will be mutually beneficial for all of us. I will start the presentation with first the objective of the workshop, how we're going to proceed. Then we're going to have I will start the first part of today's let's say lecture, and then we're going to break for 15 minutes, and then we continue with the second part of the day. So you can see my screen. Great. So as I said, I will first present the overview and the objective of the workshop. As you know, the Economic Research Forum has three main, let's say, activities. So one of the activities is related to the data collection and data dissemination, and that's why we have the OMD, which is the Open Access Microeconomic Database initiative, through which you can have access to different data sets, whether it's firm level, such as the customs data, whether it's household surveys, labor force surveys, more specific firm surveys on energy transition, on the impact of the pandemic, on the impact of the war in Ukraine. So a lot of data sets that you can use, and that also might be pertinent for the training that we're currently working on. A second pillar of ERF work is also related to the capacity building, and therefore the capacity building that we have, it takes place through the participation in our annual conference, for instance, where you present your research, and then you can get feedback on your research, and then present your work in the conference and publish it as a working paper in the ERF working paper series. Or the second pillar also of our capacity building activity is through the different training workshops that we organize at ERF. And we have several types of training workshops, ranging from microeconometric techniques like the one that we're having today. We're going to have next month another training workshop on computable general equilibrium models, more from a macro perspective. We previously had some training workshops on machine learning, on machine learning and econometrics, on financial econometrics, on panel econometrics. So, and really the objective is first to have, of all those training workshops, is first to have a theoretical background on the topic that we're talking about, followed by some empirical exercises using real data from what we have on OMD. And the third pillar of work is clearly research dissemination, and that's why we have the Middle East Development Journal, we have our working paper series, we have the forum, perhaps that you're familiar with, and if you're not, you can register to our mailing list to receive the forum, which is a weekly blog at ERF on some main topics that might also give you some ideas for your research. We have the policy briefs, the policy reports, so a lot of research, let's say, outputs with different levels of technicalities, and that might be also useful for your research. So why I'm saying this, just to contextualize a bit what we're going to do in this workshop relative or compared to our activities at ERF. For the objective of the workshop, we're going to have a 4-day workshop. So today we're going to present the fundamental problem of causal inference and why it will be more of a theoretical, the theoretical part of the course, where we're going just to make sure that we are all on the same page. So I'm fully aware that some of you have already seen this. Perhaps some of you have never seen this. So that's why, just to make sure that we are on the same page and that all the technical parts that we'll see at a later stage, we are all familiar with the background needed for that. To have an idea about the fundamental problem of causal inference, we're going to first to understand the nature of the problem itself. What are different solutions that we can have, whether it's randomization and experiments or non-experimental methods. And then to do this, we're going to mainly focus on 4 main points. First, to discuss the fundamental problem of causal inference and how it can be used in program evaluation. Second, we're going also to propose the different solutions, whether they are experimental or quasi-experimental. Third, what is the econometric theory behind, and finally, how we can apply them on state. Okay, so that's for today's program. Tomorrow's program will mainly focus on panel data models as one of the solutions that can help us overcome this problem. So we're going to see mainly 3 types of panel models, or let's say 2 large groups, which are the static and the dynamic. For the static, we're going to see the fixed and the random models, fixed effects and random effects models apply to labor force surveys. And then we are going to see the second type of panel models, which is the dynamic panel. And then we always have an application, a session for application after the break. Okay. Then for the third and the fourth day, we're going to have the second and the third solutions, which are the matching methods and the propensity scores matching method that you will see with Dr. Rasha Ramadan next week. So we will mainly see, as I said, the matching methods with its application on day 3, and then the difference with its applications on day 4. So that's basically the program of the 4 days. Clearly, this course can take up to a full semester. We do it in the masters, for instance, during the full semester. So it will really be an intensive course. We will not be able to have all the technical details, perhaps in terms of econometrics or in terms of the data applications. But just to give you, at least a first understanding of those methods and how they can be used in addition to their applications. You will receive all the material, the slides, the do files, and the readings at the end of the course. And also, in order to get the certificate of attendance, you have to attend all, the 4 days. What else I wanted to say? And then if you have any questions, don't hesitate to raise your hand or to write in the chat box. The software that we'll be using is Stata. So make sure that you have it and that it's working in order to be able to apply all the types of empirical work that we're going to do. Then perhaps before I start with the first lecture, I just want to highlight a bit or give you some important tips for Stata. What we will see, especially tomorrow, just also to make sure that we are all on the same page. Some tips for Stata that are very important when it comes to undertake the micro-econometric program evaluation techniques, whether it's for graphical presentation, whether it's to have some descriptive statistics, the multi-varied estimation methods that we're going to see, ranging from panel to PSM or to difference in difference, or the post-estimation commands. So all these commands clearly, they are, we're going to see them. And the most important thing, if you haven't worked before with Stata, is to have a very detailed and clean do file to make sure that your results are reproducible. And why reproducible? I mean that you're able to reproduce them. And why it's important to reproduce them, because for instance, if you're currently working on a paper and then you submit a paper to the journal, the referees will get back to you with some comments. And if you don't have a clear and clean do file, you will not be able really to redo the regressions in a more in a different way. So that's why it's very important to document everything in the do file. And you will see in the examples that we will share with you that the do files are very detailed, in the sense that you can work on them in a very friendly way. And this becomes really of particular importance, especially that a lot of journals now, when you submit, I mean, very good journals now, when you submit to them your papers to be published, in several cases, they ask for the data and the do files to make sure that they are that the results are reproducible from your do files. To the extent that if your results are not reproducible from the do files that you share, the paper can be retracted from the journal. So that's why having this culture of preparing a clean and clear do file is really important for your research. Okay. We're going also to see some programming skills that might be helpful for us, even if most of the commands now are ready made and already implemented in Stata. I mean, Stata 19, now we are at Stata 19. You can use another version of Stata, but Stata 19 was out like 2 weeks ago, and it's really powerful. So the need to program some commands is not very urgent, let's say, but you still can do it. And we are going to also to see quickly what are the different types of files that we have in Stata. Okay. Any questions so far? Anything that's not clear? Any queries? Does anyone want to add anything? Okay, so perhaps a couple of things also before we start, just to make sure that we understand all the technical details. As you know, we really start from the basics of the basics. In general statistics, we have two types of statistics: the descriptive statistics and the inferential statistics. In general, when we start any empirical work, we start with the descriptive statistics. And the descriptive statistics is very useful because it helps us understand the different patterns that we have in our data sets, whether our testable hypotheses are verified or not. If I'm working on, for instance, exporters and importers, whether, for instance, exporters are more productive than non-exporters. If I'm working on labor force participation, if labor force participation of women is lower than labor force participation of men. So that's why it's very important, before we start the empirical work that we're going to see during the next 3 days, is to start with some descriptive statistics and graphing to understand the different patterns that we have in the database. And that's why not only it will help us understand the different patterns that we have in the data sets that we have, but it helps us also make sure that from a microeconometric perspectives, our hypotheses are verified, in the sense that if I'm assuming a normal distribution of the error, is this the case or not? If I'm assuming that my variable, the variance of the error is constant, is that the case or not? So all this can be checked through some statistical or some commands on Stata to make sure that those hypotheses are verified. and even before we start the empirical work. And clearly, this part of all those commands related to descriptive statistics is important to first understand the different patterns that we have in the data, but also at a later stage to communicate even the empirical results. Because, for instance, now, even if we knew, I mean, for those who have already worked with state and extract tables, empirical tables from stata, the more we have stars, the more the results, we're happy because this means that the results are significant. But instead of having those large tables with a lot of numbers and a lot of stars, now, for instance, we can plot the coefficients using stata. And instead of having different numbers, we just have a figure with all the coefficients. And that's why all those graphs on stata are very important, even to communicate the results for policymakers or for different stakeholders, because it's not only the message, but the way you present the message also matters. Okay. So that's from the descriptive statistics and graphing that we'll see in the example that we're going to see tomorrow, the Egyptian labor market panel survey. In terms of estimation methods, as I said, we're going to see three different methods, which are the propensity score matching that we'll see next week, and how to make sure that the PSM is working, what we call the common area, how the matching takes place, what do we call a treatment, a control, all this. So this will be next week. In addition to this, the difference estimation and what is the rationale behind that. Then finally, as I said, the third estimation method that we'll see is the panel data method in addition to the IV, because we're going to address the IV with the panel data. So I'm currently presenting the order that we're going of the empirical work in general, because we start with the descriptives, then we move to the estimation, and after this we have what we call the post-estimation commands. And for the post-estimation commands are the different commands that we run after the regressions to test for the stability or the robustness of the results. For instance, if I want to check whether my instrument is valid or not, so I have to run a command to check that the instrument is weak or not, is valid or not, that the model is over-identified or not, and so on. After I run the PSM, I want to check whether the PSM is stable or not, and so on. So all these commands, we call them the post-estimation commands on the one hand, and on the other, they serve also in saving and extracting the results, either in terms in the form of a table or the form of a figure. So those are mainly the post-estimation commands. And finally, the final point before we conclude this introduction is, as I said, the documentation and the reproducibility, right? Because, for instance, if I'm working on a paper with Riham, for instance, right? I'm based in France, Riham is based in Egypt. We might not meet physically very frequently, but if we are co-authors and we are working together on a paper, and both of us we are working on the do file in a very clear way, this will make both Riham and myself, even if we're not physically in the same place, we can work perfectly on the do file without any problem. And that's why, as I said in the beginning, if I want to run on my own or rerun the regressions that I have already run because it's a revision, or I'm working with someone on a paper, right? We have to make sure that the results are all the regressions, I mean, are written in the do file, because it's very difficult to remember this, I mean, from your own memory and rerun everything just from your own memory, given that you might use some first difference by taking the first difference of the data. You might take the logs. If you do not document all this in the do file, it might be very difficult to reproduce the results, right? So that's why in econometrics, in general, we distinguish between the reproducibility and the replicability. We call the results or a study is reproducible if all the number presented in the study can be reproduced. And this, what we will do, Riham, for instance, will send me her do file. I will rerun the do file and I will obtain exactly all the tables that Riham has in her paper, right? And as I said, this is currently demanded in almost most of the journals, where you have to make both the data and the do files available. And there are really dedicated teams and even in some cases associate editors that handle the reproducibility and the replicability of the do files, right? And this is for the a reproducible study. A replicable study is in this case if we restudy if restudy repeats the finding in the sense that I will replicate what has been done for Egypt, but for Morocco, for instance, right? So that's why for reproducing or for replicating a paper, it's important to have a detailed do file with all the comments that, as we will see later, and all the data manipulation, the data transformation that you do to make sure that everything is tracked, either for you if you want to rerun the regressions, or for your co-author if you're working with someone, right? And that's why Stata is very useful in this regard, because it helps us use two types of files to do that, which are the do files and the log files. So the do files, it's like the main document where you write all the commands and the comments related to those commands. And you can save the do file and you can run it whenever you want. There is also the ado file. And for the ado file, it's the coding file that can be used in order to create a new command. So, so far, we have the do file, right? So it's a file, let's say regression.do. We have the ado file, and the ado in general is the type of file that is developed by developers who, for instance, you know that as we will see tomorrow, one of the commands is xtreg, right? So for xtreg, it's the command used in panel models. So we as applied economists, we write in Stata just xtreg, but xtreg is backed by a program. This program is written in an ado file, okay? And then the third type of file is the log file. And the log file is like the memory of your software, in the sense that it will help us save the results that come out of Stata. And it's useful because in general, if I work with my co-author, I can send to him or to her the log file, so he or she can read the results without having to run once again all the do file. Even if, in theory, if the do file is detailed enough, he or she can rerun the do file once again. Okay? So those are, in general, the different files that we have in Stata. Any questions so far? Anything that's not clear? Yes. Okay. Yes.
May I have a very trivial question. So you said that Stata 19, you will be using Stata 19. Is that true?
No, I will be using,
And
in my case, Stata 18, but I mean, for the commands I'm using, you can go up to Stata 14 or even 13, they will work without any problem.
okay, no, I was asking about Stata 18. I have 18, so I was asking if I'm going to get the same commands, same results, everything.
Yeah. And even
Okay, thank you.
even if you have an older version, this is not a problem for the commands that we'll be working on.
Okay, thank you, doctor.
Okay. Then also we will see in general in Stata how you can download new releases of some commands, in the sense that, for instance, if Sophia develops a new command and this command is published on Repec, for instance, then there are some commands that help you download all those new commands on Stata, either to run a regression or to extract some tables from the regressions that you have. Okay. That's basically for the introduction, and I talked also about the ADO. Any questions so far? Anything that's not clear for the introduction? Okay, so let's start with the problem of identification. So this is the first theoretical part that we're going to see today on the identification problem. And to do this, I will go through three main ideas, as you can see, a brief background, and the idea of treatment. What do you mean by treatment in econometrics? And then different extensions that help us also understand the idea of identification problem. When we talk about econometrics, it's very important always to distinguish between the causation and correlation. So from your experience, what is the difference between causation and correlation? What do you think? So don't hesitate to unmute yourself and participate. What is the difference between causation and correlation?
Yes, can I answer?
Yes, okay.
Correlation when two variables move together, like can increase when x increases, y decreases, or the opposite. But this does not necessarily mean they are causing each other. Maybe there is a third variable that contributes in causing both. But causation when one causes the other to move.
Exactly. And this is very important because in several cases, when we write papers, even, I mean, ourselves, we do not take care of this point, in the sense that in several instances we treat correlations or associations as causation, which is not the case, because as Niema, right?
Yes, Nema.
Na'ma, okay. As Na'ma said, the correlation, it's just two variables are correlated if they move together or they don't move together, but there are a kind of association between them. However, for the causation or the causality, it means that there is a sense of causal relationship between two variables, in the sense that X causes Y. And in this case, there is a reason and a result, or there is a cause and effect. And that's why, in order to be able that there is this cause and effect, we have to make sure that this causal relationship really exists, right? And this is especially important in different econometric studies, because in statistics, in most of the cases, it's more of the focus is primarily on correlations more than causation. Okay, and that's why, in general, when we want to distinguish between this correlation and causation, we have to talk about the idea of the identification problem. And the identification problem the basic definition of the identification problem is to be able to identify what is the cause and what is the effect. So the key word here is to identify, and that's why we call it the identification, right? So what does, more accurately, what does identification mean? It means basically that from the model parameters that we're going to estimate, they really capture the phenomenon within the model that we're talking about, in the sense that the model parameters or features that we include in our study, right? They are uniquely determined from the observable population that generates the data itself. So it's not due to another phenomenon that I do catch. And because if it's due to another phenomenon, in this case, I'm not able to talk about the a well-identified model, right? And that's why, in general, for this identification to let it take place, in general, it precedes the estimation, the inference, and the testing. And that's why I have to make sure that I clearly and I correctly identify my model to be able to correctly infer the statistical relations between my variables. Okay? But why in general we don't have this identification, or why we fail to correctly identify a model? The literature has shown that there is a host of reasons that might prevent us from correctly identifying the model. And I will just focus on 4 main reasons that might prevent us from, perhaps 5 also, that might prevent us from correctly identifying a model, which one basically that you have seen at the undergrad level, which is, for instance, multicollinearity, because if I have a perfect collinearity between some variables, I will not be able to identify the effect of a variable from the other. So this is a problem, for instance, of identification. Not just multicollinearity, but really perfect collinearity, in the sense that a variable fully captures the effect of the other. And if that's the case, this means that I will not be able to identify the effect of one of the variables. That's an example of when do I fail to identify correctly the model. But more seriously, because this is just the basic example that we have seen at the undergrad level, we have 4 other important reasons that might prevent us from correctly identifying the parameters that we're interested in. First is the model incompleteness. In the sense that I have a model that is incomplete. And if I have a model that is incomplete, in this case, perhaps I will have a variable in my model that captures the effect of another variable. And in this case, I will not be really able to identify that the effect of this variable on my variable of interest, right, is due to the variable that is included, because it might be due to the fact that the variable I'm including captures the effect of another variable. And this is just because the model is incomplete. To give you an example, if I'm examining the effect of, let's say, of exporters on productivity, okay? Because in general, the theory has said that there is a causal relationship between being an exporter and productivity, and between productivity and being an exporter, an exporting firm, right? So there is a two-way relationship. Let's stick to the first relation, which is the impact of productivity on exporters, okay? So the theory says that if exporters, they have a high level of, if a firm has a high level of productivity, it's able to overcome the fixed cost of exporting because it's highly productive, and therefore it can become an exporting firm. So it will shift its status from a non-exporting to an exporting firm. Okay? Which means that's the theory, right? So if I run a model where my dependent variable is the probability of exporting and my independent variable is productivity, but then I don't take into consideration the ownership structure, whether it's public or private. And we know that in general, private firms are more productive than public firms. So this means that if I get a positive impact of productivity on the probability of exporting, this might not reflect purely the effect of productivity. It might reflect also the effect of being a private firm. So if I fail to introduce the ownership structure in my model, it will the model will be incomplete, and in this case, the estimates will not be will be biased, right? Because they will not really reflect the effect of the variable in question. So that's the first problem when we can have a problem of identification, which is when the model is incomplete. Is this point clear? Any questions? Okay. The second problem is the simultaneity. And in general, this problem arises when I introduce a dependent and an independent variable, x and y, right? And they are determined jointly or simultaneously. Like, for instance, prices and quantities, right? Prices and quantities might be determined simultaneously on the market. And they might be determined through a third variable that is not included in my model, right? And that's why it can be in some cases related also to the incompleteness. But simultaneity means that the two variables of interest are determined simultaneously, and if they are determined simultaneously or jointly, I'm not really able to identify what is the cause and what is the effect, right? So that's the second problem of identification. The third problem, which is the classical problem in like 99% of the empirical papers that are published, and in general, the referees, they raise this whenever you submit a paper, which is endogeneity. And we will see this with more details, but briefly, endogeneity means basically that your explanatory variables are correlated with the error term. And if they are correlated with the error term, this means that the orthogonality assumption is not verified. And if the orthogonality assumption is not verified, then your estimates will also be biased. And we will see this with more details. But so far, we have seen three reasons that might prevent us from correctly identifying the model, which are simultaneity, endogeneity, and the model incompleteness. The fourth one is the unobservables, because I mean we do know that in most of our models we have an unobservable part related to the fact that there is a kind of unobserved heterogeneity that we don't capture. And if we don't capture it, this might also bias our estimates, and I will not be really able to identify whether the effect I obtain in a paper is really due to that or not. So that's why we have also to consider this unobservability in order to make sure that what I'm currently estimating reflects the variable introduced in the model, not something else. So basically, once again, the idea of identification is just to make sure that what I claim measuring through my model is really what I measure, not something else. And this will be like the most important point that we will try to focus on throughout the training workshop, this identification story. Okay. Moving to the second part, which is the treatment, because in order to understand the idea of identification, we need to understand the idea of treatment, right? And we're going to start with a very simple treatment where we consider a treatment, right? As you can see here on the slide. We assume that the treatment is X and we have an outcome variable Y. So here X can be a program so to support SMEs. I don't remember who said that. Someone said that you're currently working on program supporting SMEs through an RCT, I think. Right?
Yes.
Yes. So what's the program that you're currently working on to support SMEs?
We're testing the effect of different interest rates on the growth of the micro, small, and medium enterprises. So the treatment is basically the interest rate itself, giving loans with different interest rates to different treatment group, and there's a control group that doesn't get anything.
That doesn't, sorry?
That doesn't get the loan. So
okay.
This is the control group. Yeah.
So here the treatment is getting a loan, right?
Yes, exactly, with a specified interest rate.
And you're examining this on which type of outcome?
There's sales and profits.
Sales and profits. So let's say that in our case here, X is getting this loan with a certain interest rate, and our Y here is sales or profit, right? So from what we see here in the third line, the estimate beta 1 in theory should show the effect of getting this loan or not versus those who don't get the loan. Because, I mean, beta 1 here in this example, it will be just the difference between the mean Y for X that is equal to 1 getting the treatment, which is the loan, versus X equal to 0, where we don't get the treatment. So if we take the average, as you can see here, so Y1 dash, the average of Y1, right? Y1 meaning the Y of those who got the treatment will be equal to beta 0 plus beta 1, because beta 1 multiplied by 1, given that X is equal to 1 if they get the treatment. So beta 1 multiplied by 1, it will be beta 1, plus the average of the error term, because I'm estimating everything at the average, right? What we have, just a second. So what we have here. So this is Y for those who got the treatment, right? But if I multiply this beta 1 by 0 for the control group of those who didn't get the treatment, it will be Y0, which is equal to beta 0 plus the error term of those who didn't get the loan, correct? So if I take the difference between these two, so the beta 0 will cancel out with beta 0, and at the end of the day, I will get, in this case, sorry, I didn't complete this. So it will be, in this case, Y1 minus Y0, which will be equal to beta 1, plus the difference between the two error terms. So this relationship is very important for two reasons. Because in theory, if this term is equal to 0, right? So it will disappear. This means that the difference between the average of Y1 and Y0 will be exclusively due to beta 1 that reflects the effect of the treatment. So once again, if I have here my treatment, which is X, that takes that which is a dummy variable being treated or not, right? And my Y is the dependent variable. I want to make sure that the beta 1 that I'm estimating, which is this one, really reflects the effect of X or the treatment, correct? So I will calculate the effect of the treatment at the mean for those who got versus those who do not get the treatment, okay? And in this case, we're going to have this is the average for those who got the treatment. So beta 1 multiplied by 1 which will be beta 1. And then those who didn't get the treatment, beta 1 multiplied by 0, it will become 0. So the term, the beta 1 x will vanish or will disappear from the second equation. And if I take the difference between this one minus this one, so it will be y1 bar minus y0 bar, which is the difference between the average of those who got the treatment versus who didn't get the treatment. Beta 0 minus beta 0, they will disappear. And then beta 1, I will have it as it is, plus the error for the first group minus the error for the second group. So the idea now is that I want to make sure that if this term is equal to 0, and we will see the next slide when, then the difference between the two outcome variables is exclusively due to the treatment. And the treatment here is reflected by its coefficient, which is beta 1. Any questions on this part before I proceed? Anything that's not clear? Don't hesitate to ask any questions.
Doctor, I want to ask about the difference between y bar 1 and y bar 0. It means the first derivative of the second first equation. Can call it
no, here, sorry.
If we take the first derivative of y bar 1 dot, we get beta 1 plus different delta error.
Yes, I mean, basically here the beta 1 will reflect the partial derivative of y relative to x at the mean.
Yes. Okay.
Yes, but here we still don't talk about the partial derivative, because here the idea is just to compare the value itself of y1, the mean of y for those who are treated versus those who are not treated. So those who are treated, which is y1, versus those who are not treated, which is y0. Is that clear?
Yes, thank you. Clear.
Other questions? Okay, so here, that's the first idea of the treatment. As I said, the important condition here is to make sure that that there is no correlation between the different errors, right? Because here, if the treatment in general is randomly assigned, so there is no pre-selection or there is no predetermination of those who are treated or not, right? Then in this case, we can say that X is uncorrelated with the error term. So the treatment itself, which is my main explanatory variable, is uncorrelated with the error term. And that's what we call, in econometric terms, X is orthogonal with the error term. And orthogonal means that if that's the vector of epsilon and that's the vector of X, so they never meet. They never cross. That's what we call by the orthogonality assumption. And if they are orthogonal, they do like this. In this case, they are not collinear, right? So in this case, if the treatment is randomly assigned, we can say that the X is not correlated to the error term, or X is exogenous, right? Because it's that there is a kind of random assignment for all the individuals. Okay. And in this case, when can we say that that X is uncorrelated with the error term? If and only if the error that we have seen here in the previous slide of those who are treated does not equal to is equal to the error of those who are not treated. So there are no systematic differences across the treated and non-treated groups, right? Because if epsilon 1 bar is equal to epsilon 0 bar, this means in this case that the difference between y1 and y2 will be equal only to beta 1 because this term will disappear. And in this case, the only difference between those who are treated and those who are not treated is just the treatment itself, not something else. And this is very important for the identification idea, right? So if x is uncorrelated with the epsilon, if and only if the two error terms are equal to each other, right? So the e bar 1 and e bar 0. And if that's the case, this means that, as I said in the previous slide, the difference between the average of those who are treated and the average of those who are not treated will be equal only to the coefficient of the treatment, which is beta 1, right? And this clearly will give us, based on the standard methods of the ordinary least squares, an unbiased estimator of beta 1, which is the effect of the treatment on my outcome variables. So in the case that Noha was talking about, which is the effect of getting the loan at a certain interest rate, how it affects the sales of those who get the loan versus those who don't get the loan, right? So in this case, beta 1 will measure what we call, in this case, the average treatment effect, okay? Because it shows what is the average effect of the so the average effect of the treatment on my outcome variables, okay? Well, however, there is a problem because in general, we might not have this randomization. This random assignment might not be really present in our case. So if there is no randomization, nothing guarantees that the x will be uncorrelated with the error term. And if the x is if it is correlated with the error term, in this case, x can be endogenous, not necessarily exogenous. And that's why, in this case, the orthogonality assumption will be violated because in this case, the correlation between them is not equal to 0, okay? So back to our initial relationship where we have y1 bar minus y0 bar will be equal to beta 1 plus the difference between the two error terms. So if the two error terms are not equal, this means that the average of E1 bar is not equal to the average of epsilon 1 bar does not equal to epsilon 0 bar, right? This means that in this case, this shows that there is a correlation between x and epsilon. Why is that the case? Because this means that perhaps the error term in one of the two equations include some dimensions that might be correlated with the x. So the more the x changes, the more the epsilon will change, which will mean in this case that the error term for those who are treated will not be equal to the error term of those who are not treated, okay? So in this case, basically, the difference between, as long as this term is not equal to 0, right? So the difference between those who are treated and those who are not treated will not be only due to the treatment, but also to some differences included in the error term. And that's why in this case, the model is not correctly identified because I cannot claim that the difference between the sales of those who got the loans versus those who didn't get the loans in the example that was mentioned by Noha is due to the program that was implemented, but perhaps it might be due to the fact that those who managed to get the loan are more productive because they are larger firms, right? So I cannot really attribute the difference between those who are have higher sales or higher sales, or higher profits is due to the loan itself, but perhaps due to the fact that they are larger, they are more productive, they are older, a lot of things. And that's why in this case, the model is misidentified. Okay? So the difference between y1 bar and y0 bar does not estimate beta 1, but some other quantity that depends on the correlation between x and epsilon, right? So in this case, we're going to get a biased estimate of beta 1, as it will not really reflect the effect of the variable or the treatment itself. To prove this mathematically,
So
yes.
can I ask about the signal of beta 1 and the difference between epsilon 1 and epsilon 2, epsilon 0? It may be negative, or it must be in positive.
You mean this difference?
Yes.
Yeah,
And
it can be positive or negative. There is no specific condition on that.
Okay.
The idea here, and this is why it can be, I mean, we can have an overestimation or an underestimation depending on the direction of the bias itself. But the most important thing is that the difference between my outcome variables is not entirely due to the treatment itself, but due to other things that are not considered in the model.
Okay, thank you.
Okay, so let's prove this mathematically. So we know from the basics of econometrics that the coefficient that we're estimating, so B OLS, which is in our case the estimated value of beta 1, right, is equal to the covariance between y and x divided by the variance of x, correct? Or the covariance between x and x, which is basically the variance of x. So we can rewrite this as the covariance between, we replace the value of y by the value of the equation we can use it to measure y, which is beta 0 plus beta 1x plus the error term. So that's the value of y, correct? And the x, we keep it as it is. So here we have the covariance between the y and the x, right? And the covariance between x and x, we'll keep it as it is. Beta 0 is a parameter. It does not change. So it's not really of interest, right? Which means in this case that I can factorize the numerator by having I can factorize the numerator by having the covariance. So the covariance between beta 1x and x and between the error term and x. And this is what I have in this line here. So I have the beta 1 again, which is a parameter, so it can be out of the bracket. And what I still have inside is the covariance between x and x, correct? Plus the covariance between epsilon and x. So if this term is equal to 0 based on my assumption that the covariance between the error term and x is equal to 0, I don't have a problem because this will disappear. And if it disappears, I'm going to have BOLS, which will be equal to beta 1 covariance x, x, or the variance of x, divided by the variance of x. So I can simplify the numerator with denominator, and I get only beta 1, right? But that's only in the case where the covariance between epsilon and x is equal to 0. However, if this covariance is not equal to 0, right? If this covariance is not equal to 0, this means that the parameter I'm estimating will not be exclusively equal to beta 1, but it will be equal to beta 1 plus a certain term here. And that's why, in this case, the estimate that I'm currently estimating of beta OLS will be biased. Why it will be biased? Because it will not be equal to the parameter of the population, beta 1, but it will be equal to this parameter plus another aggregate, that due to the correlation between the error term and x. Is that clear? Any questions or comments on this point? Okay.
Hi.
Yes.
Is this the situation when we use instrumental variable approach?
So the instrumental variable approach helps us avoid this problem of
Yes,
collinearity
exactly.
between the error term and x. Exactly.
Because we need to find another variable that can affect the dependent variable.
Exactly.
Okay, thank you.
Okay. Other comments or questions before we proceed? Okay. So still, if we have, so that's what I have just said. So when we regress y on x, we have this relationship, and the OLS estimate of beta 1 can be described this way. So in this case, if x and epsilon are correlated, so beta OLS does not estimate beta 1, but it estimates another quantity that depends on the correlation between x and epsilon. And that's why clearly it's very important to bear in mind what are the assumptions that we have. And I think you have seen all this at the undergrad level, so I will not spend much time on that because we have already seen it, which is the assumption of the linear regression model with strictly exogenous regressors. So in order to analyze the effect of the explanatory variables on my response variable or my dependent variable, we need 5 main assumptions. So the first one, we know that in this case, the expected value of the conditional outcome variable. So yi conditional on my explanatory variable is equal to the parameter I'm estimating multiplied by the explanatory variables that we have, right? Then x's are stochastic, that the variance is constant, right? And that we have independent random variables in the sense that our variables are independent, and that the y also is normally distributed conditional on x. So all these assumptions are the classical ones, in addition to the assumption that we have on the error term, in the sense that the error has to be also normally distributed. It has to have a constant variance, which the homoscedasticity assumption, which is exactly related to that. So all those classical assumptions, they have to be verified. The one that we're interested in, I will talk about it in the next slide, but under those the first 4 assumptions that we have, right, we're going to get unbiased estimates. And we have, and you remember the best linear unbiased estimator, unbiased because the value of the parameter is equal to the value of the parameter of the population, best because it has the lowest variance, and it's linear because we're basically assuming that the parameters are linear, so to the power 1, right? So under those assumptions, we get the desirable properties of the estimator of beta 1, which include the unbiasedness and the Gauss-Markov property of the ordinary least squares of beta. But for the fifth parameter, for the fifth assumption related to the normality of y, or the error term in this case, it's just useful to be able to run all the inferential statistics afterwards, in the sense that we can run the T and the F statistic and all the tests associated with those statistics, right? Yet, I mean, the most important thing that we have to bear in mind, which is related also to the identification problem that we're talking about, is the disturbance term. And the disturbance term, which is the difference between the observed and the predicted values of the dependent variable. So the difference between y observed and the predicted y, which is x dash beta. So if we assume that the expected value of the error term conditional on x is equal to 0, here we assume that we have strict exogeneity. And that's why, based on this assumption, we will start talking about difference between strict and weak exogeneity and therefore the orthogonality assumption, right? So what happens if some of the OLS assumptions do not hold? It depends, because if some of the assumptions they do not hold, we can still estimate beta 1 consistently, but we can make inference with some adjustments in the sense that, I mean, as long as the main assumptions of the orthogonality are there, but for instance, if I don't have, if I have some heteroscedasticity in my model, this does not affect the biasness of my estimates. It just affects the efficiency of the estimates, right? So I can have some minor adjustments and still continue with the estimation. But if some fundamental assumptions like the expected value of the error conditional on x is not equal to 0, then in this case, my parameters will be biased, not only inefficient, right? And in this case, it becomes more serious. So that's why in this case, we have to consider or to bear in mind the orthogonality assumption. And by orthogonality assumption that I mentioned in the beginning, it means that the error term is uncorrelated with the explanatory variable. And in this case, if the orthogonality assumption is not verified, this means that the error term is correlated with x. And if the error term is correlated with x, this means that we have endogeneity. And if we have endogeneity, this means that the model is not correctly identified and that beta that I'm estimating are biased, right? And in general, when it comes to the idea of exogeneity, we distinguish between what we call the strong exogeneity and the weak exogeneity. So to have a strong notion of exogeneity, it means that the error term is in general independent from x, right? That's on the one hand. And in general, let's keep the exogeneity for the next slide, but the idea of to start with strong exogeneity means that regardless of without any conditions, let's put it this way, without any conditions, the error term is uncorrelated with x, okay? Without any conditions. That's the case where we have strong exogeneity in the sense that x is really uncorrelated with the error term, regardless of any other conditions we have in the model. The weak exogeneity, from its name, means that we have to impose some conditions to have this exogeneity. And that's why in this case, it's, as you can see, is if you look here at the equation that we have, where we have the joint distribution for the parameters of interest theta that we want to estimate, right? So I have the distribution for my variables y and x, right, from 1 to t. In the first bracket, as you can see here, that's the product including theta, and the second one, the second set of parameters phi. Okay. So what is the difference between the two brackets? As you can see here, we can see that here y is conditional on the different values of y, x, and theta, which is our parameter of interest, right? While the second one is the function of x conditional on the values of y, x, and the vector of parameters. So for now, we're going to ignore the second term, so this one, right? Because we are interested in the inference of theta that shows the effect of x on y, right? And that's why we assume that x are fixed or exogenous. So here, why are we talking about weak exogeneity? Because X, in this case, is weakly exogenous in the sense that there is a sense of conditionality, right? But if the error term is uncorrelated with X, regardless of any conditions that we have, in this case, it is a strong exogeneity. And that's basically the difference between the notation that you can see here for the joint distribution, where we have the conditionality and theta, right? Relative to the second one, where here, as you can see, here we have the vector of parameters phi, correct? That appear here, but here, as you can see, we don't have any kind of y, which means in this case that X is strictly exogenous or strongly exogenous relative to the model. And or in other words, to make it simpler, in this case, X does not depend on the previous values of y. While here, in the previous slide, that was not the case because, sorry, here it was not the case because, as you can see, the function of, for the joint distribution of y from 1 to t and from x1 to t, we can see that X here depends on the previous values of Y. So I cannot really talk about a strong exogeneity unless I exclude some values of the sequential or the sequence of X and Y. So the previous values of X will determine Y. So there is a certain condition, and that's why it's weakly exogenous. However, in here, as you can see, my xt does not depend on the previous values of y. And that's why here in this case, I can talk about strong exogeneity. So in other words, in a time series vocabulary, if you want, here the y does not grandeur cause x, right? Because y does not affect x. And if I'm sure that y does not affect x, regardless the timing, t minus 1, and so on, in this case, I can talk about a strong exogeneity. However, if x does affect y, but y does not affect x under certain conditions, I call this weak exogeneity. And this is summarized here in the last two lines, as you can see. For the strict exogeneity, the expected value of the correlation between the explanatory variables and the error term is equal to 0 for all S and for all T, I mean for all points in time, X is uncorrelated to the error term. However, for the weak exogeneity, the expected value of X and U is equal to 0, but for certain values, which means that in this case, I will assume that it's uncorrelated with the past values of T, okay? So that's the main difference between the strong and the weak exogeneity. Any questions on this part before we proceed? So far we have seen three key, in addition to the basic assumptions that you have already seen dozens of times, but three key points that we're interested in when it comes to identification, which are the weak exogeneity, the strong exogeneity, and the orthogonality assumption. And that the key idea for the orthogonality assumption is to have, this correlation between the error term and the x is equal to 0. So whether this correlation is equal to 0, regardless of any condition we call this strong exogeneity. Under certain conditions, we call this weak exogeneity. Any questions? Anything that's not clear?
Professor,
Yes?
sorry. I have a question, sorry, for my bad English, but
Sure, go ahead, no problem.
thank you. In the case of a purely exogenous variable, for example, an economic policy instrument such as antitrust law, to assess its impact on firm behavior, can always be applied in this case because l'instrument politique économique est strictement exogène comme variable. Thank you.
Well, this will really depend on, and this is actually one of the points that we'll talk about in 2 slides. This will really depend on econometric and economic dimensions, in the sense that here we're just talking about the theory itself. But when it comes to practice, the endogeneity problem has 2 sides, has an economic side and has an econometric side, right? And also, I will explain this in a few minutes, but it's important to bear in mind that at the end of the day, in our papers, we are economists, not statisticians. So what should drive the empirical work should be the economic theory. And in your case, for instance, for the effect of an antitrust law on the performance of the firms, for instance, well, it will depend, because perhaps a certain country did not adopt this law because large firms, they are lobbying against adopting the law. So that's why in this case, adopting the law itself will be endogenous, correct? And in this
Yes.
case, clearly, you will have to find an instrument. But finding an instrument is not just an econometric story where you will make sure that the R squared of the first stage is high, that the F test of the first stage is good, that the instrument is not weak, that the instrument is valid, and that the model is over-identified, all this, but that also there is an economic story behind. And in general, most of the instruments if you look at the papers that are well published, the instruments that are working well have also to be convincing from an economic perspective. So with an economic story behind. But clearly, back to your question, the answer will be 2 things. First, what is the answer of the economic theory? And if the answer of the economic theory that the variable might be endogenous, then in this case, you will have to find an instrument that is valid economically and after this econometrically, not only valid econometrically. Did I answer your question? Any other questions? Okay, very quickly before the break, the last part, which is very short, is the extension. And this is basically, I just want to summarize the point that I was just mentioning with Yusuf now, that in general, in most of the cases, we are interested in the causal effects, not just associations. Clearly, the associations might be interesting because we just want to know whether the associations are significant or not. But at the same time, what is important for us is this cause and effect story that we are talking about. And that's why, in order to make sure that we have this cause and effect, we have 2 solutions to make sure that the model is correctly identified. Either experimental, like what Noha was talking about, RCTs, for instance, or quasi-experimental, which is, in this case, other methods that help us, given that the experiments might be very costly, might be time-consuming, so we might opt for other methods that help us really make sure that there is cause and effect story, right? And that's why we will see after the break how we can distinguish between the two types of models that we will be seeing throughout the course. One final point to conclude this lecture, just a very brief word on what we call the structural models, because they are also important in econometrics, because in general, a structural model, it's a model based on economic theory with relations that are proven theoretically, right? And through those theoretical relationships, we can prove that there is a cause and effect phenomenon, right? And this is different from what we call the reduced form models, because in a nutshell, the structural models, I will be able to derive some relations based on the economic theory, and from those economic relations, I'll be able to identify what is the cause and what is the effect. For the reduced form, from its name, it summarizes or it compresses the phenomenon in some variables of interest, right? And I will assume that some variables are exogenous, and then we have an error term, but I have to make sure that those exogenous variables are uncorrelated with the error term. And that's basically most of our econometric work, which is more of the reduced form rather than the structural models. Okay, so in this case, clearly structural models are very interesting in the sense that they are theory based. They are not subject to the critique of whether the model is correctly identified or not, because it's not a reduced form. However, it's not always simple to work with structural models. So that's why in most of the empirical work, we use more the reduced form, right? And we try to make sure econometrically and statistically that the reduced form is correct and well identified. So I will conclude this lecture by repeating once again the point that I said when answering the question of Yusuf, in the sense that in general, statisticians, they are good at describing the data, but economists are good at interpreting the data itself. So that's why at the end of the day, even if we spend a lot of effort to make sure that our empirics are clean and clear, we have to make sure that there is an economic theory behind, and that economic mechanisms are valid. And that's why, for instance, as we will see after the break, for the IV, as long as the IV is not economically convincing, it will be, even if it passes all the tests that we can imagine, but if it's not economically convincing, it will not be able to convince the referee or the reader, and therefore the paper will not be credible, in the sense that the instrument itself is not economically motivated, right? So, and there is also a very nice paper that was published in the 40s by Koopman called Measurement Without Theory. He was really anticipating what's going to take place currently, because now with all the softwares that we have and the power softwares, and in addition to the AI that can even write codes now and get ready-made regressions, as long as there is no theory, it's not really credible to talk about economic research. So with this, I conclude the introduction of the workshop and the session. Any questions or any comments on what we have seen during this hour and a half? Anything that's not clear? Any queries? Okay, so if we don't have any questions, we will break now for 15 minutes. So now it's Cairo time, it's 5:37. We will be back in 15 minutes sharp. We'll not close the meeting. You can just turn off your mic and camera, and we'll be back in 15 minutes. Thank you, and have a nice break. Okay. Hello, everyone, again. Let's start the last part of today's lecture on the solutions. So we have seen the problem of the identification, and just to recap what we have seen. We are talking about the idea of the identification. What are the problems related to, or the reasons behind not being able to correctly identify the model, whether it's related to simultaneity, endogeneity, incompleteness of the model, or inobservability. In addition to this, we have seen the idea of the weak and strong exogeneity and the assumption of orthogonality, right? Any questions or any comments before we proceed with the solutions? Okay. So to proceed with the solutions, we will proceed in 2 stages. First, we're going to see the random experiments, and then the quasi-experiments, and then we conclude. Clearly, back to our fundamental problem, as I said, after distinguishing between this idea of correlation and causation, and how we can properly identify the cause and effect in program evaluation or in any kind of empirical work in general. We have to be able to distinguish between I'm sure that you are aware of that, but also to make sure that you are all on the same page. We have the treatment, which is the phenomenon that we're interested in, like loans, export subsidy, export program, and so on. So that's the treatment. The treated are those who will be benefiting from this program, and the control, those who do not benefit from this program. So those are the 3 keywords that we will keep in mind until the end of today's lecture, right? And again, what we're interested in is that the difference between the treated and the untreated or the control group is solely due to the program or the treatment itself, not to any other phenomenon. That's the idea of being really able to identify this cause and effect relationship. Okay? And clearly, a central point that we discussed, which is the endogeneity, in the sense that if the assignment to a certain treatment is not random, this violates the randomization point. And if we don't have a random assignment to the program or to the treatment, this means that the X can be correlated with the error term, which means that the orthogonality is not verified. We have endogeneity, and therefore our estimates will be biased. And that's why we're going to see in our solutions 2 types of solutions, broadly speaking, and that's what we will see starting tomorrow. But the objective of today is just, again, to present all the theory that we need to bear in mind, right, and all the vocabulary, and then starting tomorrow, we move forward with the more econometric details and empirical applications. So the first solution will be the random assignment. And by random assignment, we mean that we randomly assign different individuals to a certain experiment. Some will benefit, others will not benefit, and therefore the difference between those who benefit and those who do not benefit will be explained by the intervention itself. Again, similar to what Noha was talking about in the beginning of today's lecture. Okay, so that's what we call the random assignment. or the RCTs. The second type of the solutions is what we call the quasi-experiment solution. And for the quasi-experiment solution, we have a lot actually. And why we call them quasi-experiment? Because they are not experiment in the sense that we have money, time, and effort dedicated really to run a full experiment like in the RCTs, right? And then the randomized control trial. But we adopt more or less the same rationale in order to identify the cause and effect. Okay? And in this case, we have two types for the quasi-experiment solution. One that we will see mainly during this workshop, and the second one will not be able to cover during the whole workshop because we just have 4 days, but just we will have a brief idea about them today. Okay? So for the type 1 of the solution is what we call the conditional exogeneity of the placement itself, in the sense that the placement relative to the treatment itself is exogenous. And I'm going to talk about this with more details later. But we have three types or three solutions in this case, which are the propensity scores matching, the difference in difference, and the panel, right? Then the second type is what we call the type 2, which is the rules of placement, in the sense that in this case we're going to have more or less an endogenous, but let's keep the terminology for now because I will come back to all the examples later. But basically we have two solutions here, which are the regression discontinuity design, the RDD, and the IV or the control function. Okay, so those are basically all in all, we have 6 solutions to be able to properly identify a model, either an RCT, but an RCT is not always feasible because it needs a lot of resources, a lot of time. I mean, Noha, you said that you're working in GPAL, right?
Yes, correct.
And in GPAL, you can tell us on average how long does it take to run an RCT?
Yeah, the ones I was involved in, they've been, one of them were since 2018, so I think a lot of time, and another one lasted for 3 years.
So just in the RCTs where Noha was involved, between 3 and 7. No, we're talking about
8
almost
years
7
now.
years. Yeah, 7,
Yeah.
8 years, right? So it's really time consuming. It needs a lot of resources to run the different waves, to determine the control group, to make sure that there is no attrition, to make sure that the control group is not contaminated. So a lot of money and time we need in order to have a properly designed random assignment, which is the first solution, right? The 5 other solutions are related to what we call the quasi-experiments, and they are much, less time consuming, that they rely less on resources, so they don't need all the financial resources and the human resources that we need for the RCTs, because they basically use secondary data, and they depend just on the placement itself, whether we have an exogenous placement or not. And that's why we have 5 methods that we're going to see. So this is just the broad map of how to address the identification problem. Okay? Given that we will not cover technically the RCTs, I will just give an example of them and how they are implemented. Then we move to a broad overview about the conditional exogeneity of placement, okay? And then the instrument of placement itself, okay? So for the random experiments, as you know, they are the randomized control trial, and in general, the idea of the RCTs is that we want to have a random allocation of a certain intervention to a program for a treated group relative to a control group. And in this case, it's an ex-ante analysis in the sense that we will look at two groups, both are eligible to benefit from a certain program. For instance, in the example that was mentioned by Noah, I'm interested in firms, right? And I'm interested in all the firms that are eligible to get the loan. I will not compare firms that are eligible relative to firms that are not eligible. So I have to start with a sample of comparable firms. And from those comparable firms, right, I will split this group into two groups. One that I will call a control group, which will be basically the group that will not benefit from the intervention, and another group which will benefit from the intervention, which we will call the treated group, right? So in this case, as I said, the keyword here is that the two groups, they have an equal chance of receiving the treatment, ex ante, before getting the treatment itself, okay? And that's why we have a kind of random allocation, because I didn't choose between the two the two groups, some people to participate and others not to participate, okay? So in this case, the assignment process will create a treated and a control group, and clearly the two groups have to be in the beginning all perfectly, perfectly, I'm exaggerating a bit, but identical to a large extent. And in theory, we should not have any observable or unobservable differences between the two groups, in the sense that I want to start from a point where all the individuals are the same, because at a later stage, a year later, 2 years later, 5 years later, when I will do the follow-up, the only differences between the two groups will be entirely due to the treatment itself, right? Therefore, given that I did not proceed with a pre-selection of the samples, there is no selection bias, and if there is no selection bias, in this case, the randomization will help me compare the participants and the non-participants to my experiment, right? And that's why, in this case, all the ex post differences that will be observed after the intervention will be due to the intervention itself, because ex ante, everyone was more or less eligible. So that's the basic idea of the random experiment. Any questions on the random experiment before we proceed? Okay, clearly, what are the problems with experimental designs? A lot of problems, even if you know that those who developed mainly RCTs, Ster-Duflo and Banerjee, they got the Nobel Prize several years ago, given that they developed this methodology to properly identify this cause and effect argument that we're talking about. But there are a lot of problems, in the sense that, first, there are some ethical and political obstacles, in the sense that, and I'm sure those who work on RCTs, they are aware of that, in the sense that you have to bear in mind that some people will be prevented from a certain program, and they will not be able, they are not allowed to participate even over time, which might give them incentives to participate in other programs. So ethically speaking, RCTs, they face a lot of critiques in terms of that. They might also face a lot of political obstacles, in the sense that you need a lot of authorizations and permits in order to run an RCT in a country. Ethically speaking, they are not very well perceived, in the sense that your individuals are the subject of the experiment. So ethically, this might not be really acceptable. At the same time, when it comes to randomization, it might be a bit difficult to randomize at the level of individual beneficiaries. At a certain point, not all individuals might be really randomly assigned to the intervention. Then another point is the control group, because as I said, ex ante, everyone has to be eligible, but ex post, the differences will be only due to the intervention. But meanwhile, the control group can be contaminated in the sense that if it comes to their knowledge that they do not benefit from the program, they might try to do other things in order to benefit from other programs, right? So there are several incentives that those who run the experiment try to implement in order to avoid this, but in some cases, the group can be very likely to be contaminated, right? A fourth problem is related also to the treatment group to the treatment group itself, in the sense that individuals that participate in the treatment, right, might decline to participate or participate in a partial manner, which means that at a later stage, I might not be able really to follow up on how or what did the individual become after the intervention. And that's what we call the selective compliance, in the sense that it's not a full participation in the in the program itself or the treatment. Okay, so that's the problems of the randomized control trials. There are several studies that have been funded by the World Bank, by a lot of donors. I will just give you two examples, one from the labor market field and the other from the trade field. One for the Dominican Republic and the other for Egypt. That was one of the very first RCTs that were done in Egypt, right, for exporters, just to have an idea about what is done. So for the first one, which is the labor market impact of youth training in the Dominican Republic, so this RCT was between 2001 and 2005, and as you can see, as I said in the beginning, it's really time consuming. And in the Dominican Republic, they created a subsidized training program called the Jovento y Empleo. The basic idea of this program was to target youth aged between 18 and 29, where they have a classroom training, okay, and after this classroom training, they had an internship in a firm in the private sector. So that was the intervention itself, which means that in the beginning we have to choose youth between age between 18 and 29, who are all of them eligible. Some of them will participate in this program, others will not participate, which means that from this pool, they are randomly assigned. That's why it's a random, there is a random kind of random assignment. Then they evaluated, David Card and his co-authors, they evaluated this, and what they did basically in this RCT is that each time 30 eligible applicants were recruited, right? 20 of the 30 were assigned to the training and 10 to the control. So in theory, from the 30 that are eligible, we can compare the performance of the 20 relative to the 10 that belong to the control. Okay. And then from the control group, we had around 50% of the control group. They were assigned to the treatment if those that were previously assigned to the treatment failed to show up to the training at a later stage. Okay. So the training took place in 2004, and then a follow-up survey took place in 2005, more or less 1 year later. But clearly the problem is that in their study, if someone does not show up or missing the post-program data, this can also bias the results and make the results in this case non-random, because this means that perhaps those who left the program are the worst. So those who stayed are the best. And in this case, I might have an idea, I might have the impression that the program was working well, while in reality it was just due to the fact that the best students, they stayed or the best participants, they stayed in the program, while the worst, they left the program, right? So the second cohort had more participants, so around 70% were assigned to the treatments, and so around 5,000. Over the 5,000, 1,000 they dropped out or no shows, and then around 2.5 thousand they were assigned to the control, 30%, and around 1,000 from them they have been reassigned to the treatment. Okay. So that's the sample of the evaluation itself, and the outcomes that were examined were the employment, right? Whether they worked or not. What is the number of hours of work? What is the hourly wage? And whether they managed to get a job with insurance. So again, I remind you that the treatment itself was composed of two things. First, a part related to skills in classroom, and then a training, right? So it was an intervention composed of two parts. And this table here summarizes mainly the effect of this intervention that took almost 2 years. So basically, this intervention didn't have an impact on the likelihood of becoming employed, so it didn't have any impact on employment, neither the hours of work, very slight differences in monthly earnings, right, between those who participated and those who didn't participate. The difference in the hourly wage was around 10%, and no statistical difference in the health insurance. So as you can see, the intervention here was not really successful, but this is per se is a finding, and that's one of the basic argument behind RCTs is that even if the result shows that there is no significant effect, this per se is a result to avoid spending on similar programs, which can be a waste of resources. But the counter argument of what I'm saying is that perhaps the experiment itself can cost more than the program itself. So ethically speaking, it might not be, again, very well perceived, right? I'm sure that Naha might not be happy about what I'm saying, but that's what the researchers, in general, they accuse most of those who work on RCTs about that. What do you think, Noha?
No, I think both arguments are valid, and I think it depends on the context. So I agree and disagree at the same time.
Yes, so clearly it depends, and that's why we do have a lot of RCTs in different fields, in finance, like the loans, in trade, as the one I will be showing in a few minutes, in the labor market, and so on. So that was the first one. So lessons from the first case study is that randomization is very difficult. Contamination is very likely to happen because of no show-ups, because of withdrawals, because of the selective participation that we talked about. And also, especially the contamination of the control itself, right? So that's a case that's the first case study from Card and his co-authors of 2007. The second one was a bit more promising, and it was done by Atkin and his co-authors in 2017 and published in the Quarterly Journal of Economics, QGE, on the impact of exporting in Egypt, right? And what they've done, the design itself was on SMEs, given that SMEs are an important part of, they represent more than 95% of firms in developing countries. And what they've done is that the research they conducted a randomized evaluation in Fowa. Fowa is a small village in Upper Egypt, in the south of Egypt. And its population is around 65,000 inhabitants. And they are mainly specialized in carpets or clean, right? So FOA is a carpet cluster. And what they wanted to do is to see whether if they have a certain support program, they can become exporters or not. And what is the impact of that on their performance variables, right? So that's basically the idea of this experiment. They focused on the evaluation of SMEs with fewer than 5 employees. So we're basically talking about micro firms, and especially firms that were not exporters before, because they wanted really to see how this can affect them. So what they've done, they partnered with Aid to Artisan, which is a US-based nonprofit organization, in order to help market their products, their handmade carpet, right? And foster their trade relationships with other developed economies or OECD markets, okay? So they started with a baseline with around 200 SMEs regarding several variables, their production techniques, the owner characteristics, the gender, the household indicators, and so on. And they randomly selected 74 firms out of those around 200 firms to become the treated to become the treated group. And for those that are treated, they were offered the opportunity to export their carpet to the US, right, and other European retailers. And the rest of the participants, which were around 150, let's say, more or less 150 firms, they represent the control group and were not offered so the access to become exporters. Okay. The results were promising in the sense that in terms of profits and productivity, those who were offered this opportunity to become exporters, they experienced an increase between 15 and 26% of their profits relative to those who did not participate in this program, right? And then clearly, because those who are exporting, they had to produce products of better quality. They were higher quality means more expensive products, and the increase in profits was therefore associated to an increase also in the quality of the rugs that were exported, right? And this was supportive with the literature on what we call learning by exporting. Back to this period, 2007, one of the seminal paper by Benner and Jensen, they argue that firms that participate in exporting, they learn by exporting, and therefore they can become more productive because they are exporting. So, which means in this case that this RCT supports the argument that exporting can lead to a higher, an increase in the quality upgrade, and clearly even if productivity decreased a bit in the beginning, but at a later stage, it increased because of the improvement in the quality and the improvement in the increase in their sales to foreign markets, right? So in this case, we have two experiences, and as you can see in both of them, the bottom line is that it's time consuming, it's resource consuming, it has some challenges that we've been talking about, and if we do not have really the time, the resources, human or financial, to implement an RCT, then in this case we have to use the quasi-experiment methods. And for the quasi-experiment methods that we will see now, we want still, even if we don't have the resources, we want to still to identify the cause and effect argument that we have been talking about. And that's why we will not rely on experimental data. So we will not have an experiment where we have an intervention where people are eligible ex ante, and then we examine the differences ex post. But we will try to rely on some identifying assumptions that help us determine whether the individual can participate in the treatment or not, right? And in this case, the non-experimental methods in general can be classified into two types, as I said in the beginning, type 1 and type 2, depending on the identification assumption that we have. The first one is what we call the conditional exogeneity of placement, or what we call also the conditional exogeneity of the identifying assumption, in the sense that the identifying assumption itself is exogenous. Or in other words, the exogeneity is based on observables, as we will see later, right? The type 2, in general, is what we call the instrumental variables or discontinuities that can explain placement, can be found. So what is the likelihood of having this placement? So in one case, the conditional exogeneity of the placement itself, so the placement itself being placed, is exogenous. Or in other words, the conditional exogeneity of placement relative to the changes in outcome itself, so the outcome variable, right? But for the second type, in this case, it's not the placement that is exogenous, but in this case, we are looking at the phenomenon that can explain the placement itself. So that's why the placement is not exogenous. Okay, so we have to keep this in mind, because this is the fundamental difference. Between all the methods that we will see mainly in this course and the RDDs and instrumental variables that we will not really cover in details. So PSM, difference in difference, and the panel, the placement itself is exogenous, right? However, for the others, they are, okay? So that's basically the first, so that's what I was just mentioning, right? So for the type 1, that we will be interested in for this course. So as I said, the type 1 methods, which are non-experimental, so again, the common denominator between all the methods that we're going to see throughout the course, that they are non-experimental. So we do not run RCTs, given that we have neither the money nor the time to do so. Even if, I mean, and you know that perhaps you had several experiences with different journals, but even using non-experimental methods or quasi-experimental methods to publish a paper, it can take up to 2 or 3 years. But because just there are several back and forth between the authors and the referees on the instrumentation strategy, on the instrument used, and or the assumptions of PSM of difference and difference. So all this can take also a lot of time, right? So back to the non-experimental methods. As I said, for type 1, we assume that the placement itself is exogenous. What does this concretely mean? It means basically two things. First, that the placement depends on exogenous observable characteristics. So for instance, in the PSM, as you will see next week with Russia, I will, for instance, my treatment is being part of a global value chain. I'm giving a lot of examples from the trade literature, given that I'm a trade economist, right? So the treatment here is being part of a global value chain. So in order to be treated as a firm part of a global value chain, I will rely on observables to assign firms to the global value chains or not, right? So that's why the placement here, we assume that we have a conditional exogeneity of the placement. And in this case, the placement depends on exogenous observable characteristics. Or in other words, and that's why we call them selection on observables. Another example, for instance, if I want to study the effect of takaful and karama. So we have some women that benefit from takaful and karama. For those who don't know it, it's a social safety net program in Egypt. Its translation means solidarity and dignity. And it's a conditional cash transfer program. So if the women her children, they go to school and they have a regular health check, they can get financial support, right? Regardless of whether the conditionality was implemented or not. But that's the rationale of the program itself. So I will, in order to determine the treatment, the treated versus the untreated group, I have to start with, again, the same rationale of the RCTs, a pool of individuals that are very comparable. So in the sense that before they receive the treatment, right, of getting takaful and karama, all of them, they have more or less similar characteristics. So the difference is in outcome will be due only to takaful and karama. And that's the basic idea of the propensity scores matching. I will match individuals based on some characteristics, and that in this case, the selection on observables. So perhaps their age, their location, their education, and so on, to make the sample comparable, right? And we can call, so that's the idea of the selection on observables or the conditional exogeneity of the placement, okay? At the same time, we assume that we have an exogeneity of placement with respect to changes in outcomes. What does this concretely mean? It means that the unobservable factors that affect changes in outcome, they do not affect the probability of placement. So anything that I do not observe, right, and that can affect the outcome, it does not affect the fact that I'm selected for this program or not, which means that it does not affect the placement, okay? And that's why we assume also that unobservables that determine placement can affect the initial conditions, but are assumed not to affect changes in outcome over time. So in other words, something has, a dimension has to remain constant, in other words, okay? So the most important point that we have to bear in mind for the difference in difference panel and the PSM is that we have a conditional exogeneity of the treatment where the selection is based on observables. So based on observable characteristics that I have in my data. And I will try to, as much as I can, select individuals that or match different individuals to make sure that the treated and the treated group and the control group are the same before I introduce the treatment. Is this point clear? Any questions or anything that's not clear? No questions? Okay. So the example I was giving was more related to the PSM, right? The propensity scores matching that you will see with more details next week. The second type is for the difference in difference. So the first and the second difference. So in this case, as I said, under the conditional exogeneity of placement, we have the three models that we will see, which are the PSM, the difference in difference, and the panel. For the difference in difference, what we will what we do actually in the difference in difference approach is to compare the difference before and after for those who get the treatment compared to before and after of those who didn't get the treatment. And that's why we call it difference in difference, because I'm not looking at actually the difference between a treatment and a control group at one point in time. That's the first difference. So if, for instance, Hala benefited from the program, but Rihan didn't benefit from the program, and if I compare them in 2025, this is the first difference, because I'm just comparing those who benefit from compared to those who didn't benefit. But if I'm interested in how Hala that benefited from the program before and after she benefited from the program, compared to Riham, how she didn't, what was her status before and after the same points in time. And in this case, we call it difference in difference. So I'm basically looking at changes for both the treatment and the control group. Okay?
Sure.
And that's the difference in difference. Ahmed, yes?
Is there necessary before this, before starting in the first and second difference to test if the data is stationary or there is no collinearity or causality? Then we start to do this method.
Well,
Or
here the main constraint will be that you will need to have a panel data set. You cannot run a difference in difference without a panel database. But for the PSM, it's still doable with a cross section, and that's the advantage of PSM. Ideally, it can be run with panel, but even if you don't have a panel, right? You can still run a PSM, but you cannot run a difference in difference.
So the difference in difference is only use it in panel data.
Exactly.
Okay.
And perhaps also, because this will be needed tomorrow, so just a reminder also for the different types of data that we can have. So if we have T that is equal to 1, so I have 1 point in time, but the number of individuals is greater than 1, so I have a lot of individuals observed in 1 year. This is a cross section, right?
Right.
And then if I have T that is greater than 1, but N that is equal to 1, in this case, it will be time series techniques. Like I'm following a country over time, okay? Then if we have T that is greater than 1 and N that is greater than 1, in this case, we have a panel, right?
Right.
However, we have two cases here. we have the case where T is greater than N, and the case where N is greater than T. Okay? If T is greater than N, in this case, we have to use the panel time series techniques, all those techniques that have been developed by Pesaran and his co-authors on the mean group, the pooled mean group estimators, and so on, right?
Right.
However, when N is greater than T, which means that the individual dimension is greater than the time dimension, in this case, we use either the static or the dynamic panel, and generally the static panel, fixed or random effects, right? Clearly, when we have firm level data, household data, labor force surveys, we are more under this case. Why? Because in general, we have thousands of observations that are collected for some points in time. So it will be n greater than t. But if I'm working with countries, in some cases, I can have a t dimension that is greater than the n dimension. So for instance, if I'm working on MENA economies, between MENA economies, there are 22 economies. And for those 22 economies, I'm working on data over 60 years. So in this case, T is greater than N, which means in this case, I have to use the panel time series techniques. So mean group, pooled mean group, panel VAR, and so on, or panel VAC, and so on. Okay? So the panel models that we're going to see tomorrow applied at the micro level are under this group of studies, or under this group of, let's say, type of data. Okay? Any questions on this part?
Sorry, I have one simple question.
Yes.
In the case of n greater than t, is there a rule of thumb about the number of time points needed to have a proper analysis?
Well, this would really depend on the length of T itself. Because, for instance, if I have 30 countries, but at the same time I have like 35 points in time, it's still not long enough to apply the time series techniques. And why I'm talking about that? Because in general, the main problem that we can face when T is greater than N is the problem of non-stationarity, right? And in order to have a non-stationary data, we really need to have a relatively long time series. So at least 30 points in time. That's really the minimum of the T to start talking about the problems of stationarity. And that's why in the time series techniques, we can't run any time series techniques unless the sample is greater than 30 points in time. However, all those time series techniques, they work better for longer time spans compared to the individual dimension.
In the other case where n is greater than t, like most of the data sets, like ELMPS.
Yeah, no, here in this case, there is no really, there isn't any constraint, because in general, I mean, whenever you work with micro data, you will definitely have n that is greater than t, because we're talking about thousands or hundreds, and you will never be able to have micro data that is greater than 100 years.
So we can actually work with 2 points in time, only 2 points of time with the data?
Definitely. When n is greater than t, you mean?
Yes.
Yes, definitely.
Okay.
I mean, as long as you have more than a year and you're still following the same individuals, then you can work with panel techniques. And this is, for instance, I mean, in the Egyptian labor market panel survey, we are fortunate because now we have 5 rounds, 98, 2006, 12, 18, and 2023, right? In other data sets, it's a bit more challenging, like the World Bank Enterprise Survey, where we have a lot of firms' data. For Egypt, for instance, we have 3 rounds: 2013, 16, and 2020, right? But even if we have 3 rounds, the share of firms that are followed up from a round to the other does not exceed 20% of the whole data set, which means that you will work more in a pooled version, not a panel version of the database. But in general, as long as you have a relatively large sample of firms or households or individuals that are followed more than a year, then you can work with the panel.
Okay, thank you.
Other questions? Okay. Then we have seen the general idea of the type 1 method, where we have a conditional exogeneity of the placement, or the selection is done on observables, whether it's for the first and second differences, as I said, or for the PSM, where basically what we do in the PSM, and that you will see also with more details next week, we try to model the selection process in 2 stages. First, I run a probit model where I determine whether the individual is selected or not. And based on this probit model, I determine the impact of bearing in mind the fact that I'm selected, what is the effect of the treatment on an outcome variable. And that's why we match the treatment with the control groups, and to make sure that they are the same. And then the difference in the outcome variable will be entirely due to the treatment itself. But again, we're still under the family of the conditional exogeneity of the placement. And here the difference between those who are treated and those who are not treated will be called the average treatment effect. Okay? And you will also see a lot of details how we can do this matching based on which characteristics, based on which matching procedure, the nearest neighborhood, among others. But the general idea, which is similar again to the difference in difference or the panel, is that the placement itself is exogenous, and I select individuals based on their observables. Okay. The last type is the random and fixed effects. The advantage of the random and fixed effects is that we control for unobservables. And if you remember, we said that one of the problems that can lead to a misidentified model is the fact that we do not take into consideration there are some unobservables that are not taken into consideration, which will be included basically in the error term, and their inclusion in the error term will lead to a correlation with the explanatory variables, which will violate the orthogonality assumption. So that's why it's important to consider the unobservables, right? And in this case, whether we have unobservables, we do have unobservables, and their treatment will depend on whether we assume that my explanatory variables are correlated with the error term or are not correlated with the error term. And basically, if I assume that they are not correlated with the error term, in this case, it will be basically a normal OLS, which is a random effect model. But if I assume that the error terms are correlated with the error term, and I will introduce, in this case, fixed effects, then it will be different from the OLS, because basically that's the real problem that I have. For the fixed effects model, I don't need the assumption of zero correlation between the error term and the explanatory variables. Okay? So in a nutshell, the panel data models that we will see tomorrow and how they are applied at the micro level assume that after controlling for the effect of the unit, the remainder of the selection is fully observable, in the sense that given that I controlled for all the unobservables, I can control for related to the gender, related to the location, to the place where I live, to the location of the firm, to its age. All this will lead to the fact that the remainder of the selection is observable, and therefore I reduce the problem of misidentification. Okay? So for the, as I said, for the random effects model, we assume that the unobservable effects they are more or less similar to OLS, because we have to assume that the random effects are unrelated to the observable X. So the error term is not correlated with the X, and we will see this. However, for the fixed effects, they do not require this parametric assumption. So we don't need to assume that the error terms are not correlated with the X. Okay? And that's why, in general, they are relatively preferable than the random effects, because they don't need this strong assumption. Okay? So far we have seen very briefly the three types of the three methods or the three examples of the type 1 methods that are included under the family of the conditional exogeneity of placement, which are the propensity scores matching that takes place in two stages. The first stage, which is a probit model, under which I select the probability of being treated or not, and then after being treated or not, I examine the impact of this treatment on an outcome variable. That's the idea of the matching method. And in this matching method, I have to make sure that the control group is identical to or is matched with the treated group. The second family is the difference in difference. And in this case, what I'm interested in is how the individual changes before and after the treatment relative to the control group before and after the treatment. And that's why we call it difference in difference. So it's two differences, right? It's not only the difference between those who are treated and those who are not treated, but those who are treated before and after compared to those who are not treated before and after. The third type is the fixed and random effects that help control for unobservables. And at the end of the day, it will depend on how we treat those unobservables. If they are uncorrelated with my observables, then in this case, I can assume that we have random effects, basically similar to OLS. Or if I don't need to assume that they are not correlated, in this case, I will run a fixed effect. The second type of inference in the 10 minutes that we have, and because those are the ones that we will not cover in the course, are the type 2 methods. And in this case, I don't need to have a conditional exogeneity of placement. So I don't assume that the placement itself is exogenous or that the selection is based on observables. And that's the basic idea of the IV. So in this case, I assume that there is at least one variable that can affect the placement, but not the outcome. And that's the basic idea of an instrumental variable, right? And this is what we call the identifying restriction that will help me examine in two stages. First, what is the variable that explains the placement? And based on that, what is the impact of the placement on the outcome variable? Okay. Clearly, in order to have a valid IV, it must be exogenous, and we have dozens of tests that help us determine whether the instrument is weak or not, whether it's valid or not, whether the model is over or under identified. And just a sketch to remind you about that. So here, the idea behind the instrumental variable is that it needs to be correlated with the explanatory variables, but uncorrelated with the error term. Because if it's correlated with the error term, then we will still violate the orthogonality assumption. So you have to make sure that this IV is correlated with my explanatory variable, but uncorrelated with the disturbance, and they will be basically used to eliminate the correlation that we have between the explanatory variable that I have and the error term. So it's basically, as you can see in this graph. So the problem here is that my y depends on x and u, the error term. The problem is that if I have a problem of endogeneity, u is correlated with x, right? So I need a variable that will help me explain x and that is not correlated with u, which is in this case z. So z will affect x, and then x will affect y. In other words, z does not have a direct impact on y. It can affect y only through x, right? And here, as you can see, we do not have any assumption of exogeneity of placement. And that's why the IV, in this case, we are controlling for the endogeneity based on unobservables, not based on observables like what we did in the PSM and the difference in difference. Okay? So that's the idea of the two-stage least squares, where in the first stage, I examine the impact of the instrumental variable on the instrumented variable, which is the endogenous variable. And then based on this predicted value of the instrumented variable, I examine the impact of this variable on my dependent variable, right? So that's the idea of the 2SLS. One final application in the causal inference in type 2 methods, which is the regression discontinuity design that we call the RDD. And in this case, the RDD, its idea is very simple. Again, we rely on an instrument, but the difference here is that we have an instrument that determines whether an individual is eligible to participate in a program or not. And the RDD, and I will explain why we have this discontinuity, will focus on the difference in outcome around the cutoff model. How can we explain this? Let's see the example of Takaful and Karama. So as I said, Takaful IFPRI in 2018 did a study to examine the impact of Takaful and Karama program. And Takaful and Karama program, its translation is Solidarity and Dignity, which is the social safety net program. And in general, they had some criteria to let women participate in this program, which means that I have some women that are eligible and others that are not eligible. However, those who are eligible and those who benefited from the program, they perhaps they benefited from it, but they were not really positively affected, in the sense that perhaps they got the money, but did not improve their empowerment, for instance. So given that households, this program, it was assessed after it was implemented, which means that we don't have, like in an RCT, a control group relative to which we can compare those who benefited from the program, because it was already implemented. So that's why in this case, if we cannot run a randomized control trial, given that it has already started, we want to see around this cutoff of those who benefited, and I will show you a graph. Let me show you this. I think we'll not have time to cover all this. So here we have the RDD design. How it looks like, we have a cutoff for the individuals who are eligible to benefit from the program. And around this, we want to see how those who benefited have evolved compared to those that did not benefit. And the advantage of that is that even if the program has already taken place, I'm still able to determine what is the impact of the program on them, which is not the case for, because here it's too late, I mean for IFPRI by this time, to run an RCT because the program was already there. So perhaps given that we have only 2 minutes, I will talk about this perhaps tomorrow in the beginning of tomorrow's lecture, because I want to highlight some points here to conclude with the type 2 methods. So just to recap what we have seen today, and I will continue this part tomorrow. So today we have seen the general introduction of the course. We have seen 5 main concepts. First, the concept of identification and what is the problem of identification? What are the main challenges behind identification? Second, we have seen the implications of identification in terms of treatment and in terms of how we can make sure that what we are measuring is really attributed to the phenomenon that we're talking about. To address this, we have seen 2 types of techniques. Type 1 that is based on what we call the condition exogeneity of placement, and this is the case of PSM, difference in difference, and panel, that we will see. The second block does not require this exogenous placement or selection based on observables, which is the case of IV and RDD. We have seen a brief introduction of the PSM, the difference in difference, and the panel, in addition to the IV. We will see tomorrow the brief introduction of the RDD, and we continue with the panel as well as the application on data using the Egyptian labor market panel survey. Any questions, any comments, any queries? Okay, so if not, I would like to thank you all for your attention. I know that online courses, especially when they are technical, they are the second best, but we're trying to do the best with what we have. So don't hesitate if you have any questions. I think you already have my email, and if not, you have Ramaj's email, and she can send you my email if you have any questions. And then we will meet tomorrow, same time, same place, to continue with the second part of the course. Thank you all, and have a nice evening.